Good morning, everyone. This is Shauna, and I've been asked to talk in this video about slope and the relationship that slope has to equations and linear modeling. So, um, as you may or may not remember from pre-algebra or algebra, um, slope is the measure of the rate of change of um, of two variables, the y, the dependent variable, and the x, the independent variable. But it's easy to get caught up in all of the mathematical elements of it, and there are many of them. Today, I want to focus on an example that will show us the relationship that slope has to variables and to the equations themselves and where this comes from. Sometimes it's easy to think that these things arise sort of spontaneously uh, out of nowhere, but they really arise from observations a lot of times in science, in other realms, and then we use mathematics to describe those relationships. So without too much more preamble, I'm going to share my screen at this time and show you the example that I need. So if you look at this example, it says, scientists know that the rate at which a cricket chirps is related to temperature. Suppose that two pieces of data from a particular observation include the fact that when the temperature is 50 degrees Fahrenheit, a cricket chirps at a rate of 80 times per minute. And when the temperature is 75 degrees Fahrenheit, a cricket chirps at 100 times per minute. If I wanted to create a model of cricket behavior, I might start by observing the entire data set and looking for patterns. So let's assume that I've taken some data, more than just the two pieces that I've given you. I've taken observations over a period of time, and I've looked at the data. And the pattern in that data we're going to assume is a linear relationship. So for simplicity, we assume that there is a linear relationship between air temperature in degrees Fahrenheit and the rate at which the crickets are chirping. Now, the linear relationship is significant because it means that I can assume that uh, temperature, the temperature change and the rate at which cricket chirps change is constant. So it's a certain amount of rise in temperature gives me a certain amount of change in cricket chirps. So I'm going to begin by assigning some variables. Mathematical equations are one way to model observations. They're not the only way, but I was specifically asked to model the slope-intercept form of the equation. So I need equations, and for equations, I need variables. Since we want to model cricket chirps with a linear equation, we'll begin by assigning the variables where X is the temperature in degrees Fahrenheit, and Y is the number of chirps a cricket produces in 1 minute, let's say. So based on the information that I gave you in the problem earlier, when X is 50, Y is 80, and when X is 75, Y is 100. So now we get to the mathematical part of this, and slope has a lot of interpretations, some of which I'm going to give you in this little mini lesson. But slope is the change in Y over the change in X. That's one way of looking at it. And in this case, that's the change in chirping rate over the change in temperature. Now, another way to think about slope is as the steepness of a line. Now, this will be significant for you later, but this drawing is not to scale. It's slightly off. I didn't have graph paper handy, so these tick marks are not entirely evenly spaced apart. And so your y-intercept is slightly off. We'll see that when we calculate it later on. but just know that this drawing is not to scale. Um, but the slope is how steep this line is, how slanted it is. And the way that we measure slant is with the change in the y, the vertical change, over the change in x. And because we need to distinguish between our two x values, in this case 50 and 75, and our two y values 80 and 100, we use subscripts for that reason. So we have m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And the triangle is the Greek letter delta, which means change. So we have delta y over delta x. M is equal to 100 minus 80, 75 minus 50. Um, and so we get m is equal to 20 over 25, or 4/5. Now, this is where the actual interpretation comes in. So remember, y is chirps per minute. So we have 20 chirps per minute for every 25 degrees Fahrenheit of temperature. So this slope is positive. So both variables are moving in the same direction. So um, when the temperature increases by 25 degrees Fahrenheit, crickets chirp 20 times more per minute. Or if I reduce that, for every 5-degree change in temperature, in Fahrenheit degree temperature, 4 chirps per minute are increased. So slope is an average rate of change over time. Why is it average? Because it may increase by 1 degree and they may not go up exactly 4, but this is an average rate of change. This is the same thing that happens when you're on the road and you're looking at your speedometer and it tells you that you're going 50 miles an hour, let's say. Well, you might indeed go 50 miles in an hour, but that doesn't necessarily mean that over that whole hour you were going the same speed. In fact, you probably stopped a few times, you slowed down for traffic, that sort of thing. So slope is an average rate of change over time. We can say that for every 5-degree increase in temperature, the rate of cricket chirps increases by 4 per minute. And as I said, sometimes we make this equal to 1, especially when we're doing um, things in statistics, regression rates, and things like that. Sometimes we state the above in an alternate form by simplifying the ratio over 1. 4/5 is 0.8, and so for every 1 degree increase in temperature, there is a 0.8 increase in chirps per minute. So it's not quite a 1-to-1 ratio. Now, I'm going to extend this concept to actually taking us from our data and from our observations to our equation. So we recall that the equation of a line requires 2 elements, slope and the y-intercept. Sometimes the slope and the y-intercept are given to you. Sometimes one is given to you. In this case, we didn't have either one. We have to get both. We had 2 points. Sometimes these elements may be given more directly, or as in the case of our example, which I just told you, we may have to find them. When the 2 data points are given, we can use one of several methods to generate the equation. So I gave you the information again here. This is the same information that we used on the previous pages. And here's our friend, the slope-intercept form of the equation, y equals mx plus b. I'm going to choose 1 point. I chose 50 and 80. You could have chosen 75 and 100. It doesn't make a difference. Makes a difference in terms of how the math looks. It doesn't make a difference in the final result. So we put 80 where y is, because this is a point xy. 4/5 times 50 plus b, do some algebra, and b is 40. Now, we end up with y is 4/5 x plus 40. If I choose to use point slope form, I have y minus y1 equals m times x minus x1, where x1, y1 is a point on the line. Again, if I use 50 and 80, then I have what you see down below. Plug the values in, distribute on the right, and then add 80 to each side of the equation, and you end up with 4/5 x plus 40, just as you do for the other equation. So you can see that either way of doing it will yield the same thing. Now, for our purposes here, the biggest idea behind it is that we want to interpret the slope and the y-intercept. Slope is an average rate of change between two variables, and you get that from the um, data and from the interpretations that you did. So the y-intercept is the value of the dependent variable y when the independent variable is known. So for our example, when the temperature is 0 degrees, the crickets would chirp at 40 times a minute. And as you can see from the graph, this is why I said the graph was not to scale, but this point where it looks like it's about 50 should be where 40 is. It's just that my hash marks are not exact. But this should be 0 and 40, not 0 and 50, okay? Now, before I end this video, I'm gonna stop screen sharing and come back to you. So the models that we create are for giving us information about a situation. So in this case, I now have the equation, regardless of how it arose. So if I know how many times the cricket chirps, if I know the y, then I can solve for x. I can manipulate that and solve for x. If I know x, if I know what the temperature is in degrees Fahrenheit, assuming that the model holds for that temperature, then I can predict what y is. And that's part of what this issue is with slope. Now, there's all kinds of other concepts that go into slope and go into finding it and how you create it and what you do when you have points versus what you do when you have a slope and a y-intercept and how you turn things around. But this video was just to give you an overview and a sense of how these things arise from model. But slope is a rate of change of two quantities, always. And if you don't have units, because sometimes we just have pure numbers, especially when we're learning it, then the slope is a measure of how steep, how slanted the line is. A zero slope will be completely flat. It's completely flat. When you have no y change, there's no change vertically, but there is change horizontally. You get a zero slope. All the way to infinite slope, which is undefined because all you have here is y change and x isn't moving at all. So you have an infinite amount of y change over a little bit of x change. And so we have zero slope if it's horizontal, we have infinite slope or no slope if it's vertical. And somewhere in between that, we have other slope. So if your line slants upward from left to right, as ours did, then you have a positive slope. If your line were to slant downward from left to right, then you would have a negative slope. And so I hope that overview helps. If you need further assistance with slope, if you want to see more mathematical calculations of slope, please let me know. But otherwise, I hope this video has helped you. Stay well, be healthy, and I will talk to you again very soon. Thank you very much.